In this video, I am going to do a few more optimization examples from the packet that will hopefully help with the take-home quiz and also being prepared for the Unit 2 exam. So this is question 3 on page 22 of the Unit 2 packet. It says if exactly 200 people sign up for the charter flight, the fee for the flight will be $300 per person. If more than 200 sign up for the flight, each fare will reduce by $1. Now, this should really say like for each additional person that signs up for the flight, each fare will be reduced by $1. So like if 201 people sign up for the flight, then it's reduced by $1. But if 202 people sign up for the flight, then it's going to be reduced by $2. So it's for like each additional person, they're reducing the fare by $1. Determine how many passengers will result in the maximum revenue for the agency. Also determine if the fare needed to maximize revenue and the amount of the maximum revenue realized. Okay. So again, we are trying to maximize revenue. So we need to come up with a formula for revenue, R of X. And again, in this case, for our revenue, we are going to use the whole idea of taking X, which in this case is the number of people, times the demand function, which again, we can call P of X or D of X, whatever you want to do. So this would be our revenue formula again, and we're going to say X is our number of passengers. And then P again is the demand, the price demand function. Okay, so P does represent kind of, I guess I'll just put the price of the fare, but we're going to write our price demand function with our P. So again, when we do our price demand curve function, it is going to be linear because each time for each additional person, our flight is reduced by 1. So again, we have a constant slope, so it's linear. So we can again use that formula mx plus b because it's a line, and we need to find the slope and we need to find the y-intercept. So again, I'm going to write kind of 2 points, or you can just think about how much it's going up and down to find the slope either way. But we know if exactly 200 people sign up, the price will be 300. And again, my X is the number of people, so that comes first. And then the P is like the Y value, so that comes second. Sorry, this should be 200. And then we're saying for each additional person, like if more than 200 people sign up for the flight, and like I said, it really should say for each additional person. So if I have 201 people, the fare is going to be reduced by $1. So it'd be 299 if I do 300 minus 1. So using those points, I can find my slope using the slope formula. So I would do my y2, or in this case, p2 minus the y1, which is actually p1 in this case, and then x1 minus x2. And so I get -1 over 1, which is -1. Okay, so again, we know the fare is reducing by $1 for each additional person. So that's why it would be -1. So I'm going to place that for my M. And then I need to find B, and you can use either point. I'll just use the 200, 300. So my price was 300. Then my number of people is 200. So I plug those two values in, and then I solve for B. And so I would add 200 to both sides, and I get B equals 500. Okay, so my price demand function is going to be P equals -1x, or you can just put -x plus 500. That's my price demand. And then if we do our revenue function, which is what we're trying to maximize, so we always take the derivative of what we're trying to maximize, which is revenue, is going to be x times this p of x function. And then again, it's completely up to you, but I generally find it easier to just distribute because it's not that hard to distribute here. My x, and then I don't have to use product rule and I can just use power rule when I take the derivative. So I distributed the x, I just put the negative instead of the 1. You can write the 1 if you want, it really doesn't matter. But this is my revenue formula, which I'm trying to maximize. Anytime I'm trying to maximize or minimize something, we find the critical points, which means we take the derivative and we set it equal to 0. So the derivative of negative x squared is negative 2x plus the derivative of 500x is 500. I'm going to set that equal to 0 to find my critical points. So I would subtract 500, or you can also add the 2x, whichever way you're more comfortable with. And then I'm going to divide by negative 2. Okay, and I get x equals 250. So this is the number of people. I'm going to make sure I have a max. So just to verify I have the max, I go back to my first derivative and I'm going to take the second derivative. So using, here's my first derivative. The second derivative is negative 2 and then 500 is 0. And anytime my second derivative is negative, that means at that x value, or I mean, at any x value that we plug in, pretty much, my function is concave down. So it's always concave down for this case because I get a constant. And anytime it's concave down, the critical point is a max. So x equals 250 is a max. Okay, it's only at the critical point that we have a max when it's concave down. That's an important point. So let's see all what they asked me. Okay, so they said how many passengers, which we found was 250, determine the fare needed to maximize revenue and the amount of the maximum revenue. So it doesn't matter which one we do first. For the fare, we use our price demand function and plug in our 250. So again, my price demand function is this, okay, and my revenue function is this function. So we're going to plug in 250 to both of those to get the two answers. So I would plug in 250 and simplify. So this gives me, my price would also be in this case $250. And then my revenue, I would plug in 250 to this revenue function. And just when you're doing this, make sure you don't have the negative in parentheses. You're only squaring the 250. And if you do that, you should get, this would be 62,500. And we should put units with all of these. So I'm going to add passengers to 250 because that's what it represents. So we would need to, in order to maximize revenue, we would need 250 passengers and then a fare of 250 would be charged, and the maximum revenue earned would be the 62,500. So again, just make sure after you do the derivative and you find the critical point and verify that it's either a max or a min, you make sure you answer all of the parts, because generally these questions ask multiple parts. So you'll need multiple answers. Okay, so let's look at another example. So this example says when you have 30 orange trees are planted on an acre, each will produce 500 oranges per year. For every additional orange tree planted, each tree will produce 10 fewer oranges. How many trees should be planted to maximize the yield? So there's actually two different ways to set up this problem. We can set it up by doing what we kind of did in that last one and find the price demand function, multiply that by X, and do that. You can also set this one up kind of like we did question 2 when I did the strawberry farmer in the video before. And if we do that way, though, the only thing is we would be like finding the additional number of trees. So if you do it that way, you would have to add how many initial trees there are, which is like the 30 trees. So I will set it up both ways and you can kind of pick which way you're more comfortable with. So for the first way, just in general, if we talk, we're trying to maximize again, to maximize our yield. So again, with our yield, I'm just going to call our yield our revenue. And to maximize our yield or our revenue, we would, to find our total revenue, we would take the number of oranges, like each tree yields. And we would multiply that by the number of trees. Okay. So if I want to find the number of oranges for each tree, and again, we can use whatever letter you want, but we'll just say P again. This, if we look at this, we start with 30 oranges being planted, and then they'll produce 500 oranges. And for every additional orange tree planted, okay, so when the number of trees goes up by 1, each tree will produce 10 fewer oranges. So the output will go down by 10. So again, this is linear because each tree, we're going up the same amount of trees and down the same amount of oranges produced. So it's a constant slope. So for each additional tree, so if I plant one more tree, which means I'd have 31 trees, each tree will produce 10 fewer oranges. So 500 minus 10 is 490. I'm going to use this to find my slope. So I would do 490 minus 500 over 31 minus 30, which again means my oranges are going down by 10. My trees are going up by 1. So my slope is negative 10. Okay. And if you don't want to come up with 2 points, you can just do the change in the number of oranges over the change in trees, and that would give you the slope the same way. And then again, I'm just going to use P, and again, it's mx plus b because it's a line. And let me just define my variable. So x is going to be the number of trees, and p in this case is going to be the number of oranges that each tree yields or produces. Okay, so we found our slope to be negative 10. We have to find b by plugging in a point. So again, I usually just do the initial one, but it really doesn't matter which one you plug in. Okay, so we get 500 equals negative 300 plus b. I would add 300 to both sides, and I get b to be 800. So I would get P equals, for my equation, if I just come up here, P equals negative 10x plus 800, okay? And then again, we said our revenue, we would take that and we would multiply the number of trees, and the number of trees is just X. So I would distribute again the X, so I don't have to worry about product rule, and I get 10X squared plus 800X. I would take the derivative, because again, I'm trying to maximize revenue. So at any time we're trying to maximize or minimize something, we take the derivative. So my derivative of negative 10x squared is negative 20x. 800x is 800. I'm going to set that equal to 0 and solve for x. So I would subtract 800. I would divide by negative 20. And I get x equals 40. Okay, and again, we're going to put the units. So this represents 40 trees that would need to be planted. And that's all they ask, actually. So that's all I need to find for this problem.